Greetings and welcome. This is Dr. B.D. Vaisulu, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the derivation for frequency and time period of compound pendulum. The course outcome of this topic would be compute the time period and frequencies of simple, compound and torsional pendulums using the basics of free and forced vibrations. The topic covered would be derivation for frequency and time period of compound pendulum. The topic learning outcome is understand the concepts of free and forced vibrations with simple harmonic motion and apply them to field problems. Before going to the compound pendulum condition, let us first do the derivation of time period for the conical pendulum condition. As shown in figure, in conical pendulum, the mass attached to a cord will rotate in horizontal circular path of radius r. As you can see here, this is the pendulum fixed to the roof or some support, and this bob will be making a circular movement in this fashion for a horizontal plane. In a horizontal plane, the movement of the object happens. The rotation of the bob is making or happening in a horizontal plane. And as per the given data here, the length of the pendulum is L and the acceleration to gravity and mass both combined, weight of the bob is mg, and the centripetal force is given as Fc, and centrifugal force is given as Fc, and the height, perpendicular height from O is being considered as h here. So as per the given data, let us see the figure. The centrifugal force Fc is given as mv square by r, that is equal to mr square omega square by r, where v has been replaced with r square and omega square. That means v has been replaced with r omega, where we know v is equal to r omega. Then we can write Fc is equal to m omega square into r, where the r square term, r gets cancelled with the denominator r here. So we can write Fc is equal to m omega square r. Taking moments about O, we can write Fc into h, that is Fc acting in this direction, horizontal direction, and the perpendicular distance between this moment center to the force acting, line of action, is h. So we can write the moment of Fc with respect to O as force into perpendicular distance. Okay, so that is the case here, which is being considered in LHS. Fc into h is equal to mg into r, where mg is acting vertically downwards here, and the perpendicular distance of this mg with respect to O is r as considered here. So that can be given in the RHS part. So we have been obtaining it to the equation Fc into h is equal to mg into r. So from this, as we have the value of Fc as m omega square r, we can substitute that value here in this equation, that is equal to mg into r. When we simplify this, we can write omega is equal to under root g by h. So the time period, which we have the equation as 2 pi by omega, that is equal to 2 pi by under root g by h, which we have obtained just now, the value of omega, that gives the value of 2 pi by under root h by g. So the time period of conical pendulum is given as t is equal to 2 pi under root h by g. Now coming to the compound pendulum. First, let us understand what a compound pendulum is. Compound pendulum is a rigid body oscillating about a fixed axis through a point other than the mass center of the body. As you can see here, let us take an example of a steel rule, which we know that is being hanged to a nail on a wall. Okay, hanged to a nail on a wall. Steel rule will have a certain hole here for the hanging of that steel rule purpose. And let us say it is the center of mass or centroid of the steel rule is somewhere here present, determined with C. and it has been hanged at some other position, hanged at other position other than the center of gravity or centroid, and it has been moved to one way, or it has been moved to one side, and it is released, then what happens? It will make the oscillations. It will make the oscillations in to and fro motion like this. Okay, so this to and fro motion causing oscillation is termed as the compound pendulum. That means this body, the total body which is being used, or which is having the simple harmonic motion or the movement with respect to the hanging point, is termed as the compound pendulum. So the compound pendulum is a rigid body oscillating about a fixed axis through a point other than the mass center of the body. As you can see in the figure, the mass center is at a distance of B from the hanging point, that is O, and it is being lifted or shifted to a inclination of theta as shown here, and there is weight and forces acting as shown in figure. So we can draw the forces triangle here, which will show the values of the hypotenuse sides of the triangle, and from this we will get the values. So restoring force F is equal to mg sin theta. The restoring force F is equal to given as mg sin theta. This F is equal to mg sin theta is being obtained from this here, where the force F which is acting in this direction is being taken like this, and the mg sin theta would be the component of that mg force. The moment of F about O can be obtained as F into B is equal to mg sin theta into B. That you can observe in the figure, the moment which is considered, and the turning moment can be given as I into alpha. The turning moment which is represented with I into alpha, which is obtained as mg sin theta into B is equal to mk square into alpha, where I is equal to mk square is the term used for the mass into radius of gyrations plane, that is moment of inertia. So if we further simplify this, we will obtain the value of g into theta into B is equal to k square into alpha. So from this, the value of alpha would be g theta B by k square. Then time period is given with the equation t is equal to 2 pi under root displacement by acceleration, where we have seen the value of omega as under root acceleration by displacement. So here the time period is t is equal to 2 pi by omega. So in the denominator part of the omega, we are writing under root acceleration by displacement. When it comes to the numerator, it will be changed as shown here. T is equal to 2 pi under root displacement by acceleration. So when you substitute the values of displacement, that is theta, which is being given to the compound pendulum, and the acceleration value, that is angular acceleration value obtained there, g theta into B by k square, and when further simplification is done, the value will be obtained as t is equal to 2 pi under root k square by gb. So the time period of simple pendulum can be given as 2 pi under root L by G, where by comparison we can say that L is equal to k square by B. So this is the time period of compound pendulum, where the equation will be obtained as t is equal to 2 pi under root k square by GB. So this concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.